get started. I'll begin with a word of prayer here. I think it's time to get started. Excuse me. Dear Father, we thank you for this day. Again, I thank you for this class and just ask you to guide our steps, help us to understand a little bit more about RC circuits and how to analyze them. Lord, in your name I pray, Lord Jesus. Amen. Lest I forget, here's the attendance sheet. I'll let you do the honors. So today let us look at a circuit like so. Let's see here. And we'll put R1 here, we'll put R2 here, and capacitance here, and E. And we'll assume that the switch closes at t equals to 0, and the charge Q on C is 0 for t less than 0. All right. So then the question is, analyze the circuit, see what happens, right? Okay, so let's see here. So how should we do this?
How should first figure out the voltage drop at R1? After R1?
The voltage drop at R1.
After R1.
After R1. Yeah. Let's see here. So we can think about, I mean, I think I agree with that. But we should probably think about some currents, right? Like maybe this is current 1, and this is perhaps current 2, and over here, current 3, right? After we close that switch, there's a current, right? Let's see here. And if we do that, excuse me, goodness gracious. Then I have Kirchhoff's voltage law. Let me put my plus minuses in. So I got minus, plus, current 1 goes here, right? So I go plus to minus, like so. Plus minus for current 2 here, right? And, excuse me, I think we can also say that I3 should be dq dt, right? With a positive because it's going to be increasing the charge on capacitor 3, right? Starts out at 0, and then as the current 3 flows, the charge builds up on the capacitor. So we know that. All right, so how are I1, I2, and I3 related then, guys?
I2 plus I3 plus I1.
Right, I1 is I2 plus I3. I think that's the natural Kirchhoff's voltage, Kirchhoff's current law. Actually, we're finding the current. We're applying Kirchhoff's current law here at that node right there. And I also can say that, excuse me, goodness. Let's see here. So I've got E minus I1 R1, right? Let me put the loop. So I'm doing Kirchhoff's voltage law like this, right? Let's see here. So then I have what? I have also minus I2 R2, right? And I think that's it for that loop, right? And what else can you see here? I mean, we could write down, you know, a loop equation, but I think when I have something like this, I've just got two elements that are in parallel, you know? So it's more natural to me there simply to write down I2 R2 equals to what? The voltage on the capacitor, right? And the voltage on the capacitor is what?
Zero beginning, starting.
Well, I mean, C is Q over V. Right? So I would say it's Q over C is what I would say there. I don't think it's zero though. Well, that's a good question. Is the voltage on the capacitor? I guess it's zero. I guess you're right. The voltage on the capacitor is zero to start with. Yeah. And if the voltage on the capacitor is zero to start with, what's that say about I2?
It's probably more than zero.
It's zero, right? So when I close that switch, what's that?
You said I2 is zero?
I2 is zero, yeah. It has to be, because otherwise there'd be a voltage here. So if the voltage on the capacitor is initially zero, because it has charge zero.
But the voltage on the capacitor is initially zero because that switch is open.
Yeah, but it's still zero afterwards because VC is equal to Q over C. And that I can't, in an infinitesimal time, change from no charge to finite charge. So the charge being zero beforehand means charge zero right afterhand, which means the voltage right after I close the switch on the capacitor is zero, which is to say that all of the voltage is being dropped across R1, all right? And current 1 is actually equal to current 3 right after I close the switch. It has to be because the voltage drop here is I2 R2. And if this wasn't zero, then that would mean that there's a voltage on here, which would mean that there's a finite charge on here, which is impossible immediately after I close the switch. Now, as time goes on, the situation changes, right? Eventually, what happens is this is like an open circuit, and this is just a voltage divider. So like, you know, like all the current just flows through here, and none flows over here because it's been charged up to its maximum voltage. But we should work this out, right? I'm just telling you what happens. Let's do the math. So how do I do that? Let's see here. Goodness gracious.
Rebecca, where were you at?
I'm sorry, what? What?
What were we trying to figure out?
We're trying to figure out the currents as a function of time.
Okay.
Uh-huh. Yeah, I mean, our goal is to find I1 and I2 and I3 as functions of time. So we've got three equations, right? This, and this. And two of them are algebraic, and one of them, well, there's four equations, I suppose, right? Because there's this one, too. Sorry, guys. Can I eliminate, so what I'd like to get my hands on, I want to eliminate one of the variables, right? How should I do it? I suppose I can do, I tell you what I'm going to do. I mean, there's many paths, but I'll just go down one of them. So like this, I can swap out for E minus I1R1 minus I2R2. But what is I2R2? It's Q over C, right? So I can just say minus Q over C rather than I2R2. All right. That's kind of better. And I'm not sure it's exactly what I want yet, but on the other hand, I also have that I1 is what? Up here, right? So I can trade this for an E minus I2 plus I3 times R1 minus Q over C equal to 0. Now I know that I3 is like dq dt, so that's what I want to keep, you know? So I like this because I know that I3 is dq dt. I'm trying to eliminate everything except for I3 and q because those are both part of the same story. Oh, but I can trade, check this out, right? This tells me that I2 is what? It's equal to Q over R2C, isn't it? So I can trade out this I2 R1, right? And what am I up against here? I'm up against E minus, apparently, Q R1 over R2C minus I3 R1 minus Q over C equal to 0. Well, this is great because this is the kind of equation we can solve. Let me rewrite it over here. So we have, let me put everything, let me leave E on one side and put everything else on the other side, okay? So we've got I3 times R1 plus, let's see here, 1 over C times 1 plus R1 over R2, I think, times Q equals to E. Are you guys with me? Does that algebra track for you guys? If I made a mistake, do let me know. So I factored out the 1 over C. All right, great. Then let us divide by R1, and we get dq dt plus 1 over 1 over C times 1 over R1 plus 1 over R2 times Q is equal to E over R1. All right. This is a linear differential equation, right? Can we solve this?
Yes.
Yes. So what's the solution?
You have to use the integrating factor.
I could, or I could do this. Lambda minus 1 over C times 1 over R1 plus 1 over R2 equal to 0 implies that the characteristic value is just 1 over C times the sum of R1 over 1 over R1, 1 over R2. Let me just make that a definition. So therefore, Q is equal to like some constant, C1 times e to the lambda t, plus a particular solution. But the particular solution here, we should put in the form a constant. And so then QP prime is 0. I plug that in. I get QP prime plus this lambda times Q is equal to E over R1, which tells me that my QB is equal to yowzers, E over lambda R1. So therefore, Q of t is equal to C1 e to the lambda t plus E over lambda R1. This dark magic I'm using is called differential equations, if you're wondering. Some of you are in it, and we just did this morning. So, yay. But now I'd like to have, what's Q of 0? You're like, I don't know what you're doing. That's okay. You can solve this, like you just said, with the integrating factor method. You guys can do that. But I'm going to do the easy way. All right? So Q of 0 is, see, oh goodness, C1 plus E over lambda R1. So lo and behold, I have the solution. I think Q of T is equal to E over lambda R1. So I've got E over, now this is lambda, right? So I'm just going to like go ahead and do R1 over C times 1 over R1 plus 1 over R2. That's my E over lambda R1 term. See, this says C1 is minus E over lambda R1. So that's why I'm writing this. And I simply have E to the lambda T. But lambda is this pesky 1 over C times 1 over R1 plus 1 over R2 times T. Minus 1. Now I've definitely done something wrong here, right? Oh yeah, you guys see what I did wrong? Let me fix this. So like I know this is crazy because my solution is an exponential, a positive exponential in time. But that's nuts, right? As time goes to infinity, the charge goes to infinity. That's not right. Where's my mistake? Check it out, it's right here. So what I'm doing right here is writing down the characteristic equation for this differential equation. So like that plus is supposed to be a plus down here. So that's my mistake right there. That should be a plus, which means that there's supposed to be a minus right here. And there's a minus here. And that doesn't, none of this changes, except that there's a minus. Well, I made my lambda minus, so that, excuse me, my bad. I put the minus in the lambda, so that's fine. So there's supposed to be a minus here, and I guess, excuse me. Oh man, I guess that there's a minus down here if I haven't made a stupid mistake. Let me get away from the board and think about it for a second. All right, so if I do that, then let me be less weird and rewrite my answer in like a more natural way, which is E goodness times C divided by what is it 1 plus I think R1 over R2. I put the minus through here, so I get a 1 minus E to the, minus 1 over C times the sum of the reciprocals times T. So there we go. That's the charge on the capacitor as a function of time, if you believe me. Let's check on whether or not this makes sense or not. So, excuse me. Does this check with what we expect intuitively speaking? First of all, at time when we check t equal to 0, we get 0, right? That's good. We should like to see that. And if you set aside, the capacitor being here, what should the voltage be across R2? Like the voltage on R2 should be what? It should be the current through R2 times R2, right? But the current should be E divided by what? Now I'm assuming there's two ways to look at it. The one way is before the switch is closed. The other way is after the switch is closed for a long time. But I'm saying, suppose no current goes through the capacitor. You know, what I call that I3. Suppose I3 is equal to 0. Then the voltage on R2 should just be IR2, right? But what's the current in that case? Well, the current we can get from the equivalent resistance idea, right? So the total resistance is R1 plus R2. So if I take E divided by R1 plus R2, that should give me the current in this situation. So that's that. Which would be also what? E over, 1 plus R1 over R2, right? By algebra. And so if the voltage on the capacitor is equal to the voltage on R2, and that's equal to, of course, what? Q over C, right? So if we have that, so this we should see for time going to infinity, we should see this kind of result. Do we see that? See what happens when time goes to infinity here? With Q divided by C is E over 1 plus R1 over R2. So indeed, it checks. My solution checks with that limiting case, as we'd hope. All right. Eventually, the capacitor charges up to this like voltage. And I say eventually it does. That's a lie, of course, right? All I can really tell you is that the time constant of the circuit, for about 5 of those, it's over 99% charged, right? And then it takes an infinite time for actually to reach this voltage in the limiting sense, right? What is the time constant for this circuit? This one's a little bit different, right? So for this circuit, the time constant right here, it's you have to look at this as minus t divided by tau. If we put what's here equal to minus t over tau, that essentially defines the time constant. And so if you look at it, it's got to be, I think it's like, oh man, I can't do math today. I'll be very, very lazy. It's 1 over, it's one over, good grief. 1 over C times 1 over R1 plus 1 over R2. That's the time constant here, I think, which of course you could write as, C divided by the sum of the reciprocals of the resistance, which I think you could simplify further, right? It would just be what? It would be like R1, R2, C divided by R1 plus R2. I mean, that might be the best formula for the time constant in this case. I don't know. That's kind of funny. It's almost like there's a parallel resistor. Like these resistances are in parallel with respect to the capacitance in some sense. Funny. Anyway, I don't have a good intuition for why that happens, but I'm sure some of you, after your engineering degree is done, will understand it more than I do. That'd be great. Anyway, so great, we found the charge. Now what next? How do we find current 3? So the path should now be clear. I3 is dq dt, right? We got Q, we differentiate. So I3 dq dt, which is what? Oh, it's unpleasant, isn't it? So it is EC over 1 plus this 1 plus. Oh man, I can't read anything. R1 divided by R2. That times the derivative. What do we got? Of e to the lambda t minus 1. And what's that give me? EC over 1 plus R1 divided by R2 times lambda e to the lambda t, which I believe probably would pay off to have left Goodness gracious. Probably would pay off to put the other formula back in terms of lambda too, huh? Oh, I'll just deal it. I'll just work it out. E times C over 1 plus R1 divided by R2. My lambda was minus 1 over C times the sum of the reciprocals, right? E to the lambda t, I'll just leave it like that. So what happens here? The c's, they be canceling. And I think I should rewrite this as this and this simplify, right? Let's see here. So if I factor out R1 from that, right? I get that. So then, with that done, I'm sorry, the algebra seems harder than it is because I've made some poor choices along the way here. But I think I get minus E over R1 times E to the minus, golly, what was that lambda? E to the minus 1 over C, 1 over R1 plus 1 over R2 times T. I'm not sure I like this answer though. So that's allegedly my I3. What do you guys think about this? I don't like the minus. I feel like I've got an error somewhere, guys. I feel like I3 should be positive.
You use E lambda to the lambda t minus 1 instead of 1 minus E to the lambda t. Like you used to do.
Oh, thank you. Very good. Perfect. You got it. So I was supposed to have a minus here and a plus there, right? Yeah, thank you. Excellent. So we just put a minus in front of all this, which changes this minus to a plus, plus. There we go. I feel much better about this answer. Thank you. I knew it should be positive. I mean, like, just physically speaking, it's clear that it should be positive in this situation. Now this makes sense, right? How does this work? How does this work? I3 at t equals to 0, what do we have? We have I3 of 0, just a little bit after time 0. That's our notation for this, right? 0 plus just means, technically it means t equals to delta, where delta is greater than 0, but a very small positive constant. But let me just say 0 plus for the sake of, not making this into a Calc 2 class or something, or worse yet. So this is just E over R1, right? The exponential of 0 is 1. So the initial current is E over R1, which is just what I was telling you guys at the start of all this. It's as if the capacitor is a short circuit. There's no voltage dropped across resistor 2. Total current, E over R1. And what happens as we get time going to infinity? This is 0, because the capacitor behaves as an open circuit for large times once it's charged up. Does this make sense? I mean, so this problem's a little bit scarier than the last one we worked because, it's got like a system of equations and there's a differential equation. We have to figure out how to eliminate variables to find a differential equation to solve. So yeah, it's a little bit trickier, but it's the same principles that we've been working on like the last 2 classes or so. Now that I found I3, how could I find the others? It's fairly straightforward, I guess, what to do at this point, because I2, we can go back to this equation And we can get I2 from that, right? So this would tell me what I2 is. I just go to my Q formula, multiply by 1 over R2C, and that gives me, you know, I2 is equal to E over R2 plus R1, I suppose, times 1 minus E to the minus T over tau. So there you go. That's what I2 is as a function of time. Now, does that make sense? How about time 0? And notice what goes on here, right? I2 of 0 is 0, because 1 minus 1 is 0, which is just what I was telling you. Current 2 is 0 at time 0. No current flowing over here. What's the current at infinity? Basically E over R1 plus R2, which is just what I was telling you in the intuitive double check of the formula over there. After a long time, no current flows through the capacitor essentially, so it all flows here, which just makes this the series circuit with R1 and R2. So that checks, right? And then how would I find I1? I just add these two guys, right? And what is I1? That might be kind of amusing. So I1 of t is I2 of t plus I3 of t. How's that work out? Is it anything pretty? Where was my I3? So I've got E over R1 plus R2 times 1 minus E to the minus T over tau. That's my I2 formula. I3 we figured out was E over R1 times E to the minus T over tau. So let's see here, what's that? So that's equal to, you know, we've got E over R1 plus R2 plus, you know, E times 1 over R1 minus 1 over R1 plus R2 times E to the minus T over tau. So there's current 1 as a function of time, which I suppose you could answer various interesting questions about using that formula, like, you know, when is the current 1 is the total current in the circuit, right? So when is the total current largest? Can we answer that, or is that too hard a question? I don't know. We could think about some questions like that, but there it is. It is a function of time, right? It's not the same, because the capacitor is different in terms of, you know, the energy that you're taking from the circuit, right? What I would expect is that the current is decreasing as time goes on, and it's largest at the start, right? Because basically you're charging up that capacitor, but after a while you'll charge the capacitor up. You stored the energy that you stored there, and then you're just going to be dissipating energy in the resistors at a pretty much steady state past 5 time constants, approximately speaking. But anyway, that's it. That's the example for today. Do you guys have any questions about it or anything? So I thought it would be nice for you guys to have like a little bit more time to talk amongst yourselves with the group project, I mean the mission. So you can talk to each other about that now, and you got 15 minutes. You should be able to do something. Yeah. Uh-huh.